So this video is to help you get started in the hand simulation exercise that you'll do during Lab 2. This is very similar to an exercise you'll do in the homework, but in the homeworks we've put a random amount of time between individual arrivals. So in the homework you have, say, I think a customer arrives, and then there is another single customer arrival sometime in the future, but the time in between the customers is randomly varying. In this particular example, we know that every minute another batch of muffins arrive, but the number in each batch is what's being variable. But it turns out that when you hand simulate, the fundamental way that you go through the simulation is identical, although the schedule appears to be very different. So in the lab, we've given, depending on actually your student ID, sort of the last digit of your student ID, you've been given a different schedule of muffins, like this one, where you have a number of muffins shows up initially, a number of muffins shows up 1 minute after that, a number 1 minute after that, and so on. So here, 7 muffins arrive initially, then a minute later 4 more arrive, then a minute later 11 more arrive, and so on. And you are to simulate the experience of those muffins as they come through for 2 different policies for when to put them into the oven. A greedy policy, in which if the oven is available and muffins have arrived, you immediately put that batch in the oven, as well as any others that might have been waiting before the oven is available. And you can do that up until you reach 30 muffins. If you try to put more than 30 muffins in the oven, you'll have to create a partial batch, and I'll show you how that works here a little later in the video. There's also the nearly full policy down here, and in the nearly full policy we actually wait until you have at least 20 muffins waiting for the oven, and then you start the oven. See, in both cases the oven takes 3 minutes to complete. And so there might be some arrival schedules where it's actually better to put the muffins in immediately rather than waiting. But in other cases, it might actually be a better idea to wait until you have a large batch. That way you can cook a bunch of muffins at once rather than cooking a small number and having a bunch queue up while those are baking. So that's what we'd like to compare, these 2 different policies. That's the idea here. Okay, so there are 3 types of events. So what I've done here is you see the spreadsheet in front of you. This is the Lab 2 help example spreadsheet. I've made this available on Canvas. It has 3 tabs down beneath here. Example, which is what we're going to be working on. Solution set, which I click over to. We can see that's where this has already been completed for. And then this scratch pad over here. And that scratch pad is where I can sort of take notes as we go if I want to sort of outline some different formulas or anything. So I have the scratch pad opened up here in another window. So if I type in this window, like this is a test here, it will also show up over here on this tab down here. So after I'm done with this video, I will then update the spreadsheet online so that if you download the spreadsheet online, you'll get exactly things where they left off after this video. Alright, so let's get rid of this text here, which gets rid of it over here, and go back to our example. Alright, so a discrete event system simulation is driven by whatever is in its future event list, or the FEL. And these are a list of records. Each event record stores the type of event. It stores usually a time associated with when that event is going to happen, and then possible auxiliary information we need to to actually execute logic associated with that event type. So there are 3 types of events in here. There are arrivals, in which case the event record will look something like A, and then a time, and then a batch. So as an example, I might have A, 1, B, 1, which would be the arrival at time 1 of batch 1. Now that's maybe a little redundant, and if I look at my solution set, we can see that, if I look at all of the arrivals, A1, B1, A2, B2, A15, B15, I can see that in this particular example, all the arrival events, the middle number, the time of the event, will always match the number of the batch. And that's just because we've scheduled the batches so that they come in one every minute deterministically. But in general, this isn't necessarily the case, which is why we'll stick with this convention, even though it's got the information showing up redundantly. And then we have departures. And so those look like D, and then the time of the departure and the batch that is departing. And so as an example, you might have D5, B6. And the way I would read this is that this event record represents the event of, so let's make this something like more like D15. So this would indicate that batch 6, which is the batch that arrived at time 6, departs at time 15. So that gives me enough information to work with when I finally have to process this. And then the last event is the end event, which is just E and then the time, where the time is when we're going to stop the simulation, so E30. So this event isn't generated by the system. This event is artificially inserted so that we know when to stop the simulation. So in this particular simulation, I think I've told you, and I'll check my solution set to be sure, yes, I've told you that the simulation ends at time 30. So in this first line, before anything else, I'm going to do an E30, just to say that I know that there is somewhere on the horizon, there is the end of the simulation happening at time 30. Okay, now I know my first, the event that I'll have to process is an arrival of this batch. So there is a batch 0, arrives at time 0, and brings with it 7 muffins. So then I have to say, for the greedy policy, what's going to happen? Well, the initial conditions for the oven is that the oven is empty. So I can say initially, just for my, just to keep things in mind, the number of muffins in the queue is 0. The number of muffins in the oven, in S, number in the service, is 0. The oven line is empty, so maybe I'll just put open parentheses, close parentheses, and then the instantaneous utilization B is just going to be 0 divided by 30, or 0, because the instantaneous utilization is defined as the number of items in the server divided by the total capacity of the server. So the instantaneous utilization is initially 0. And then there's the total time in system, the total number served, and the integral under the instantaneous utilization curve, and the maximum number in the queue. So all of those are equal to 0 initially. So I guess I could write those out if I wanted. So maybe over here, these are the state variables, and then my performance variables here, my performance measures, I know that these all start at 0. B and max in queue. All right, so I have to say, well, what happens on an arrival event with the greedy policy when, as it says over here, there is nothing in the oven? The oven is sitting on idle. Well, in the greedy policy, we just put them directly in the oven. So that means that the number in the queue is going to stay at 0, and the number in the server is now going to go up to 7. So there are 7 now being serviced. There are 7 items in the oven. And so for the instantaneous utilization, I can just calculate, well, 7 divided by 30, and that gives me my instantaneous utilization of about 23%. Now, the total time in the system, I can only update the total time in the system and the total number served on a departure event, because these calculate based on the departed number of muffins, how much time has been accumulated with them in the system, and how many of them were there, and none have departed. So these stay at what they were, which I can look over here, and they're initially 0. So I'm going to put a 0 and a 0. And then this int B is the integral underneath the B curve. So if I were going to maybe do a little drawing here, I could maybe draw an axis here. This is a time axis, so maybe I put T here, and up here maybe I'll put B for the instantaneous utilization. And so like this is maybe time 1, this is time 2, minute 1, minute 2, and so on. And the instantaneous utilization, it starts at a particular value. It's going to, it starts at 0 actually, from 0 to 1. And then, or in this case, it actually doesn't start, it starts a little higher than 0. But you can imagine it starts somewhere, and then at the next minute, it jumps to something else. And the next minute, it might jump to something else, and so on. And so int b is the area underneath this curve. So I can maybe draw these little lines indicating it's the area underneath the curve. And so that is going to be the new area in the rectangle that is being added by this line, plus whatever int b used to be from the previous one. So this, if I get out of the drawing mode here, the int b formula is always going to be like the previous int b plus whatever the utilization currently is times 1, where the utilization is the height of the new rectangle, and 1 is the width of the rectangle, because we're using 1 time unit is what we go forward in. So I can then say, well, my instantaneous utilization here is 0, which was the initial integral under the instantaneous utilization, plus then whatever the instantaneous utilization is times 1. And max number in the queue, well, the previous max number in the queue, what starts out initially, is 0, and now there are still 0 in the queue, so this stays equal to 0. So then the oven line. So the oven line helps us keep track of the ovens in the order in which they are in line. So in this particular case, we add this batch, B0, 7. So this record here means batch 0 has 7 muffins in it. And whatever's at the leftmost of the line is in the oven. And then we count over NS number of muffins in the oven line, and whatever batch is to the right of that are waiting for the oven. So here we've got none waiting for the oven. We got 7 in the oven, so that's what the oven line looks like. And so this length of the oven line is always going to be the sum of NQ plus NS. So now that we've maintained we've got the oven line updated, we've got these state variables updated, what other things do we need to do? Well, we've had an arrival and we've put the muffins in the oven, so that means they're currently baking, and so we've started an activity. Whenever you've started an activity, you must schedule the end of that activity, or else the simulation will never end the activity. So we now want to go up to the future event list, and we want to generate a record which is going to account for this batch 0 leaving the oven. It's currently time 0. It takes 3 minutes to do the baking, so we're going to schedule a departure event 3 minutes, which is just 0 plus 3 ahead for this batch 0. There's one other event that we now have to worry about. Since we scheduled an arrival, we now need to worry about the next arrival. And so we are then going to schedule the arrival of batch 1, which we know is going to happen at time 1. And so I'm maintaining the order of timing in this future event list for convenience. So the future event list should always be in order by time. So A1, D3, E30. Alright, so now I'm done with the arrival event of batch 0. So I now need to move on to the next event in the future event list, which it says here the next event is the arrival at time 1 of batch 1. So I'm going to copy my future event list down, because I know that most of those are going to be preserved in the next line, and I'm going to process the first event, which is A1B1, the arrival of batch 1 at time 1. So I'm going to delete that from the future event list, And I just have to remember that I am currently processing an arrival. So I'm at time 1, and I've had an arrival of 4 muffins. So I have to ask myself, what can be done? Well, it's the greedy policy, and so I can see that there are currently muffins in the oven. The oven is busy. I cannot stop the oven, so I have to keep the same number of muffins in the oven, 7, which means these 4 muffins can't be added into the oven. They have to wait, so they go into NQ. The instantaneous utilization is still going to be equal to the number in the oven divided by the total oven's capacity. It can store 30, so 7 over 30. Total time in system and number that have left service, have been serviced, hasn't changed because we haven't had a departure event yet. So I'm going to leave those at 0. Integral underneath this instantaneous utilization curve is just going to be equal to the previous plus the current utilization times 1. And then the max number in the queue, well, now I know the previous max was equal to 0. And if I look now, I've had 4 in the queue. So that means I have to update that, so it'll be equal to 4. The oven line, it starts out, because I haven't had departures, with the ones that were in the oven. But now I can also add batch 1 waiting on them. So now remember, this oven line, the way we interpret it is we start in the oven on the far left of the oven line, and I count over the total number that are in the oven. So if I go to the oven line, I see that if I count over 7 muffins, I'm right in between these 2 batches, which means the batch on the left is in the oven and the batch on the right is waiting for service. Okay, so this is an arrival where I cannot schedule a departure event because these muffins did not get into the oven because the oven was busy. So the only thing I have left to schedule is another arrival event. And so I go to my future event list and I think, all right, when's the next arrival event going to happen? The current time is 1. They arrive every minute. So the next arrival event is going to be 2, and it's going to be a batch 2. And it'll get inserted in front of that departure event. So then I'm done. And I'm done with that. All right, so let's just, for a sanity check, go to our solution set to see if I've messed anything up. Looks like I match the solution set currently. All right, we'll go back to our example. And so now we're at clock 2. And so things will get interesting here once we have this final departure event, which is coming up here. So now I've had an arrival of 11 muffins, but the oven is still busy because we haven't had a departure yet. So the number of muffins in the oven stays at 7, but now I've got 15 muffins waiting. That's 11 plus 14, so 11 plus 4. So that's where I get my 15. So the instantaneous utilization is still 7 divided by 30. These are still 0 because I haven't had a departure. The integral under the instantaneous utilization is the previous plus the current times 1. And then now the max number waiting, well, it now has increased again. So it has to go up to 15. We can copy our oven line down, but we now need to add in batch 2, 11 muffins to it. Future event list we can copy down, and we just processed the arrival of B2, so that's gone. Those muffins are went into waiting, so we can't schedule a new departure yet. So all we can do is schedule the arrival of batch 3 at time 3. And now I can move down to the next, to time 3. So in time 3, we're at time 3, and now we've got 2 events that we have to process simultaneously: the arrival of batch 3 and the departure of batch 0. So I may need to do some intermediate calculations here. So if I were to process the arrivals first, I can say, well, in the arrival case, I haven't had a departure yet, even though the departures will happen. So I can leave this at 7 temporarily, and I can say that I had an arrival of 8 more muffins. So 15 plus 8 means that I have 23 waiting. And I could go through and calculate this instantaneous utilization, but because I've got this other departure event happening, and because the instantaneous utilization is just calculated from the number in the muffin oven, I'm not going to bother with it right now. These I would normally be 0, but we're going to do a departure event, so I'm going to leave them alone for a bit. And then the max number in the queue, it's not really fair, again, for me to update this, because this is based on the history here, and I still haven't processed that last departure event. So I am going to at least temporarily update the muffin line to include these new 8 muffins. So if I temporarily bring this FEL down and I say, well, I processed the arrival of the batch 3, now I need to do the departures of batch 0. And so what happens when these depart? All right, well, one thing that happens is if we have a departure of batch 0 and there are 7 muffins in the oven, I can get rid of those 7 muffins that are departing, and the total number served is going to go up to 7. Well, I guess technically it's going to be whatever was previously there plus 7. The total time in system, this gets a little more complicated. The total time in system is just the previous total time in system, and then this is going to be the total time in system by a muffin for every muffin that departed. So for this particular case, I've got, this is batch 0, and so we know that batch 0 muffins arrived at time 0, and they've left at time 3. So I can simplify this by saying that they have spent 3 minus 0, they arrived at 0, they departed at 3, and there were 7 of them. So that's what I'm going to put in this TTIS. It's going to be the previous TTIS plus the 7 that departed times the time in which they spent. And they left at 3 and they entered at 0. So they spent 3 minus 0 in the system. So I've got 21 in my TTIS. Okay. So that was their departure. Now that they've departed and the muffin oven is empty, then I've got these 23 muffins that I can move into service. And so I can switch the NQ down to 0 and increase the NS to 23. And I can do that because there are 30 spots in the oven, and so I have these 23 waiting, and so I can shift them directly into that. Now if I calculate my instantaneous utilization, it jumps way up. If I calculate the integral underneath that curve, it's going to be this times 1 plus the previous one. The max number waiting, well, that's still going to be equal to 15 because now there are none waiting. And I can now get rid of that departure. But I do need to schedule the departure of this new 23. And so I now have 3 batches simultaneously living in the oven being baked at the same time. So I need to actually schedule 3 departure events all for the same time in the future. So I need a departure for batch, and so this will all happen at time 6 because we're currently at time 3 and it takes 3 minutes to bake. 3 plus 3 is 6. So I've got a departure of batch 1, a departure at time 6 of batch 2, and a departure at 6 of batch 3. And the last thing I need to schedule is an arrival, because there was an arrival on this line as well. And so the next arrival is at time 4, and it's of batch 4. And so there we have it. So that has, we've now processed all the arrivals in that time and all the departures in that time, and then we would have to move forward into the next event, which the next event is an arrival. So I'm going to skip ahead here. Let's look at the scratch pad, and I'm sorry, not the scratch, the solution set, and let's see if I agree with me so far. So if I'm looking at, in my solution set here, if we just finished the time 3 case here, and 21.7, 1.466, 15, and then the oven has got batches 1, 2, and 3 all in the oven. We've got the arrival at time 4, the 3 departures, and the end time. So that's, so far, I've shown you how we get up to this point in the list. So you can keep going through this process, processing the arrivals and the departures. The only other really interesting case is one that comes if we go, so I'm going to look down here to what happens. If you notice, in the solution set here, there are, at one point here in the oven line, there are 2 batch 6s. So we have to ask what happened there. So what I'm going to do is I'm going to copy my solution set all the way down to batch 5 and just sort of jumping ahead. So if I paste that in, it's as if we did all of this down to here. And I am now going to do what happens here at clock 6 to see what happened with this oven line and how this oven line suddenly gets these 2 batches that have the same ID. It's the creation of these partial batches. Well, let's see what happens at time 6. So I just copied my future event list down so I can see all the things that happen at time 6. And it looks like at time 6 we get an arrival of batch 6 and we get departures of batches 1, 2, and 3. All right, so let's just do the departures first. So departures of batches 1, 2, and 3, that's going to wipe out 4 plus 11 plus 8, 23 muffins. So suddenly we're going to have 0 muffins in the oven, and our oven line is going to be depleted of those 3 batches. Now I have to, the number in the queue at the moment is just going to be, would just be 11 plus 12, but because I have an arrival event, I'm not going to worry about that right now. That was my departure event. So now I have to keep track of those 23 that just departed. Well, 21 plus 23, I guess I could do that in Excel. So if I take my total number here, that's whatever number departed before plus the 23 that just departed. So I have 30 total that have departed. My total time in the system is going to be whatever it used to be plus, and then here I have to keep track. So this is a complicated calculation. So let's just go back to the scratch pad where I can plan it out ahead of time. So it's going to be the total time in system plus, and then I need to add the experience of the 3 batches that have just departed, and they've come from different arrival times. So batch 1 departed, and batch 1 arrived at time 1, but it's departing in time 6. And I know that batch 1 had 4 muffins in it. So we have 4 muffins departing at time 6 that arrived at time 1. Batch 2 is also departing at time 6, but it arrived at time 2. Batch 2 has 11 muffins in it. So 11 muffins departed at time 6 and came in at time 2. And then I've got this third batch that arrived at time 3, departing at time 6, and there are 8 muffins. So that's going to be 8 times 6 minus 3. So that's my little scratch pad over there planning this out. So let's go and then just implement that. So the previous time in system plus 4 times, and I'm just reading from my scratch pad. All right, so 109 is our current total time in system. Okay, so we've just processed those departures. So we now would like to then schedule muffins to go into the oven. So let's keep track of, so we've got these muffins that have been patiently waiting. So 11 plus 12, well, that's 23 muffins are waiting to go in the oven. And then we have an additional arrival from a batch 6 of 10 more muffins. So the number in the queue waiting is technically 11 plus 12 plus the new 10 muffins, 33. So if I put 33 here temporarily to say that they're waiting, then we can say, well, how many of those can we put in the oven? Well, the oven only can fit 30. So the best I can do is put 30 in the oven, and the other 3 I got to leave outside the oven. So if I go to my oven line, I can start by, I normally would have put in B6 10 there to say that there's a single batch of 10 muffins that arrived at time 6. That's kind of what B6 means, arrived at time 6. What I want to do now is actually split that batch into 2 partial batches, where we have one batch of size 7 and a second batch of size 3. And by splitting that batch of 10 into 2 batches, one of size 7, the other of size 3, both marked as arriving at time 6, then that allows for these 3 batches, 11 plus 12 plus 7, to add up to the 30 that I can put in the oven. And the partial batch, these are the unlucky muffins that have to wait until the next cycle. Okay, so now I can calculate my instantaneous utilization. That's easy. It's just 30 divided by 30, so it's equal to 1. My integral underneath that curve is just going to be the previous one plus the current times 1. The max number, well, that's going to be, what's bigger, the previous 23 or the current 3? Well, 23 is bigger, so I'm going to leave it as 23. Now, in my FEL, those 3 departures can be removed. I'm sorry, yeah, those 3 departures, those are the previous departures, 1, 2, and 3 can be removed. But I need to schedule, and actually this arrival can be removed, but I need to schedule the departure of the batches that I just put in the oven. So there's going to be a departure at time 9, that's the current time 6, plus the service time 3, that gets me to 9, of a batch that arrived at time 4, batch 4, a batch that arrived at time 5, batch 5, and a batch that arrived at time 6. And that might seem ambiguous because it looks like we have 2 batches called B6, but if you keep in mind that the batches, their name is really just keeping track of when they arrived, then it's okay that I have 2 batches that are called B6, because this is clear that it's referring to the batch that is in the oven, and there's only one B6 that's in the oven, and that one came in at time 6, and so later we'll be able to calculate the total time and system from that. So those are all the departure events, but I also need to schedule an arrival event. So there's going to be an arrival event at time 7 of batch 7. So now I'm done with that entry. So this we've got the next arrival, these 3 departures, the end event, our oven line. Just to make sure we didn't mess anything up, let's go to the solution set where this has been done before, and I see 10, 6, 3, 31, 109. 10, 6, 3, 31, 109. That's all good. 34, 23, those 4, and then these 5. And then 34, 23, those 4, and then these 5. So it looks like we've been doing it correctly. So you can keep on doing that all the way down through, and eventually you would end up getting this entire solution set. So I guess I could copy this and pretend that we did everything. And then you're left calculating these performance measures for this run of the simulation. And that is just going to be equal to the total time in system. For this average time in system, well, that's just the total time in system divided by the total number that have been serviced. And the average instantaneous utilization, well, that's just going to be the integral under the instantaneous utilization curve divided by the clock. And so our last clock was 30. And then the maximum number of muffins that were ever waiting in the line, well, that's just equal to 23, because that this sort of is monotonically increasing, and so that was the worst we got. Go over to the solution set, see if that agrees. Looks like it agrees. So that's how you do the greedy policy. So there's also the nearly full policy, which is nearly identical, except that when you empty the oven, whether you schedule a departure event or wait depends upon how many are currently in the queue. And so if there are fewer than 20 in the queue, you do not schedule a departure event on a departure event. So if I was to go over to the solution set, because I know this video has already gone 35 minutes, and so I'm sure you probably don't want me to walk through this whole example again. But if we look through the solution set here, then what we can see is that there should be times when there are no, like in this case here, there are no muffins in the oven, and muffins arrive. But those muffins don't get put in the oven even though the oven's idle. Another arrival comes, and there now are more muffins waiting, but now no muffins have gone in the oven. So if you look at the future event list, at the end of the first arrival, we just scheduled the second arrival. At the end of the second arrival, we just scheduled the next arrival. It isn't until this arrival of batch 2, the third arrival, because I start from 0, that I get 11 muffins, where the 11 muffins that were waiting plus the 11 new muffins add up to 22 muffins. And so at that point, I finally have more than my threshold of 20 muffins. And so I can now put those into the oven, and then those oven line, the oven line that relate. So here's all of those 3 batches that went into the oven get 3 departure events, which you can see right over here. So the only difference between how you do the greedy policy and the nearly full policy is when to ask yourself, is it time to schedule departures? Is it time to put muffins in the oven? In the greedy policy, whenever you get arrivals and the oven is empty, you schedule departures up to 30 muffins. In the nearly full policy, you have to have a number in the queue plus a number of arriving that goes above 20, or is 20 or more. And if it goes above 30, you got to do the partial batch thing the same way we did up here. And there might be some partial batches that get generated in this sample. Just scanning through here, and I don't see any partial batches initially, but there's probably, it wouldn't surprise me if there are some in here. But again, I don't see any off just glancing at this real quick. But you could potentially have partial batches in the schedules that we've given you. Once you're done with all of this, the formulas for these are identical to the formulas for these. You're just using different data. And so notice that even though I had the same schedule of muffin arrivals coming in, I get different performance coming out here. So it's a deterministic policy for when you put muffins in the oven. And we have the same number of muffins coming in at the same times. But those two deterministic policies nevertheless have different performances. So up here in the greedy policy, for this set of muffins that came in, we had a line that went all the way up to 23. So in the nearly full policy, maybe it's not as much of a surprise that the line didn't ever get more than 22. It's not that much of a difference, but it is a difference. We can also see that the oven utilization is roughly the same here, but the average time spent waiting per muffin in the greedy policy here was actually almost a third of a minute less than it was in the nearly full policy. So it looks, at least from this particular schedule of muffins, that the nearly full policy actually makes the muffins wait a little bit less in order to get baked. But it's going to be hard to tell without doing several more replications with different schedules of muffins coming in. All right, hopefully that is helpful. So what I think I'll do is I will post this set as it is, or maybe what I'll do is I'll get rid of, maybe I'll just put the first 5 lines and I'll leave those kind of completed, similar to what is done in the set, and the greedy one I'll just leave empty. So this is what I will update, and you can give this one a shot on your own. And you've got the solution set right here. You've got the notes I've been making over here. It's just a copy of what's going on over here. So hopefully that's helpful. If you have any other questions, feel free to send us an email or post something on the Canvas discussion board.